So the impetus of this really came back from, like I said, I'm a practicing bridge engineer, and we think about the theory of reinforced concrete. We know that all the concrete that's in tension is going to crack, and basically it's holding the reinforcing steel in place. It's holding the shear reinforcing, the tension reinforcing. But you're going to get flexural cracks and shear flexural cracks that essentially result in like an arch analogy or a truss analogy, where we know there's a compression load path that's going to carry the applied loads over to the supports. So the whole idea behind this was, can we develop a beam where we get rid of all the concrete that actually doesn't serve any purpose? And the simplest embodiment, this is about a 18-meter beam we did on a project up in Maine back in 2009. And so what you see is when you put the shell in place, it's self-supporting on its own. Then we fill the concrete in the rib to get the compression arch. The deck is placed after that, and ironically what happens is when you place the deck, you actually pre-compress the concrete, which is to your benefit because concrete doesn't fail in compression. Concrete fails usually in shear or tension. So by pre-compressing the concrete, we actually maintain the capacity of the concrete at a higher level as we get to the ultimate limit state. I'll show you that later. If we put a quarter-point load test on here, what we see is that we get the compression going down the arch, steel tension tie along the bottom, and then the shear is actually carried in tension field action along the webs of the FRP until we get to the ends of the beams where it begins to be carried by the concrete arch and fin. So it's really quite a fascinating load mechanism. This gives you a good example of comparing an experimental load test to a finite element analysis using Abacus with some very high level contact surfaces and nonlinear elements. And you do actually see the tension diagonals for the shear develop from the load point out as opposed from the bearing in, which is sort of counterintuitive what we do with steel, but again, it's basically because of the load sharing mechanism between the FRP webs and the reinforced concrete. When we design them, we actually just design them as a reinforced concrete beam. So the limit states we typically check, we're going to look at the live load deflections, which generally controls, and we solve that problem just by adding more steel. Then we look at the ultimate bending capacity and then also the ultimate shear capacity. And the way we do that is we just develop, we look at strain compatibility and force equilibrium just like we would a reinforced concrete beam. But now we've got a lot more components because we've got the FRP components, we've got the strand in the bottom, we've got a top flange, a bottom flange, the concrete flange. But still, we can look at the linear strain distribution and calculate the forces in each one of these components. You can set the horizontal forces equal to 0, sum for the moments, and you get this nice simple equation that gives you the ultimate neutral axis of the beam. And that's something that'll keep you busy on a Friday night when you've got nothing better to do. But I'm kind of lazy, so I look at it this way. Compression is equal to tension. Compression is equal to 0.85 F sub C prime AB, which is Whitney's equivalent stress block. And our nominal moment capacity is just the horizontal force times the moment arm. And this is what we would do with concrete, right? And if we do this equation, you can basically neglect the FRP shell in the calculation, and you'll get within 5% of the answer, and you'll always be on the conservative side. We always do the rigorous calculations so we know what the actual capacity is, and it checks out very well in the laboratory. But again, in terms of just simplicity and being able to quickly design one of these, you can go that route.